How uranium generates electricity. So when we're talking about a nuclear power plant, we're talking about generating electricity from uranium. So in order to understand that, we need to understand what is nuclear fusion. Okay, when two atoms collide and combine to form a larger and heavier element, energy is released in the form of heat. The sun is a nuclear fusion reactor, converting hydrogen into helium. Okay, so we're not able to do fusion. We've not figured that out yet. Fusion is combining elements. Okay, you're fusing them together. What is nuclear fission? When an unstable isotope of radioactive elements is split into two parts, energy is given off in the form of heat. Okay, this is what we know how to do, fission. Okay, and so the way that I think of this is you're breaking apart an atom, it's fizzling apart, fission. And what is radioactive decay then? Radioactive decay is when an unstable isotope converts into a smaller, more stable element. The process is called radioactive decay. Okay, so that's what this image on the bottom is showing us. This is triggering fission. So the little arrow with the blue ball hitting the larger atom represents an electron being shot at this atom, which makes it unstable, and it breaks it into two different atoms. So when that split occurs, a huge amount of energy is released, and that is the heat that heats up the water in a nuclear power plant, which causes steam to rise, which rotates the generator. So when the uranium atom is split, heat is released. The heat is used to boil water to steam. The steam is used to turn a turbine in an electric generator. 20% of the U.S. electricity is nuclear produced. Some of the other countries around the world that use more nuclear energy are France, which has 80% of its energy needs are fulfilled through nuclear power, and Switzerland gets 50% of their power from nuclear sources, but it is not without risk. Spent reactor rods currently get stored on site in power plants until the storage question is resolved. So the storage question is how and where to store nuclear waste. It's partly a scientific question as far as what area is going to be geologically stable and safe, but more so it's a political question because it seems like nobody wants to have this nuclear waste in their backyard. So of all of the nuclear power plants that we have in the U.S. and around the world, there's no good answer for this storage question. How do we dispose of nuclear waste? Because it stays radioactive for so long, it really is a long-term risk. Geologic setting for uranium. Uranium atoms are large and they don't fit into many minerals, so it's not strongly held in many rocks, meaning it becomes mobile. Okay, so this first image, we're looking at a roll front. When it's mobile, the uranium can be carried by low temperature waters, so it occurs in several different geologic settings. Most involve groundwater picking up uranium in one place and depositing it in another. So for the roll front, you get an arcuate or irregular boundary between two types of groundwater. So the groundwater flowing in from the left side is uranium rich. It hits another body of groundwater that is not, and you get uranium deposited along that contact, and so that's called the roll front. Another area of deposition is in a breccia pipe. These form as caves collapse with later introduction of uranium into permeable breccia in the pipe. So the broken up pieces of rock in the middle are where it accumulates. That's the breccia pipe. Also along unconformities, this type is mostly Precambrian in age. So it's thought to be because atmospheric conditions were so different then than they are today. So you get large deposits of uranium collected at unconformities, again, during the Precambrian time. And so some issues associated with nuclear energy. The first one, we've got three. Uranium can contaminate the water, land, and air around the mining facility if poorly handled. Miners can become ill due to overexposure to radioactive material as well. Okay, so you can contaminate the water, land, and air, and the miners can get sick. Number two, after the uranium fuel rods are used up, they're still radioactive and must be stored. Okay, number three, a reactor meltdown such as Chernobyl or the close call in Japan after the most recent earthquake can contaminate a large area. Alright, so here is our turbine generator. It's just a coiled wire between a magnetic field. When the coiled wire spins, electricity is generated. So this is the same thing used at a coal power plant as used at a nuclear power plant. It's the same idea. You heat up water and the steam spins this coil between a magnetic field, and that's what generates the electricity. So water is used to spin the turbine. Okay, in most cases as steam, but in some cases just as liquid water. So water is used to spin the turbine. Okay, in the case of a hydroelectric dam, you have the act of the water falling generating the electricity here. And just like the rest of our power sources, there are advantages and disadvantages of hydroelectric power. Advantages being primarily you have no greenhouse gases emitted from a hydroelectric dam. You also don't have any greenhouse gases emitted at a nuclear power plant. So those are two great things. But there are some drawbacks as well. But before we get into that, I'll just explain how this works. So a hydroelectric dam stores water behind the dam. The dam captures water and sends it down chutes from a high area to a low area where the moving water spins a turbine. An advantage to dams is the potential energy of the water can be stored until the electricity is needed. And you can't do that in most cases when you're generating electricity. You would need something like a battery, but in this case you can store that up. And 10% of the electricity in the U.S. is coming from hydroelectric power. What geologic factors are important when building a dam? Okay, you need to have a narrow, deep reservoir to minimize evaporation and provide drop, right? Because it's that fall, it's gravity's force that is spinning the turbine. So the bigger the fall, the more energy you can generate. The valley walls should be relatively close together. It should be relatively impermeable rock beside and beneath the dam, right? Because you don't want your water flowing out of the dam. It should be able to retain it. And a deep, narrow reservoir loses less water to evaporation. The side rocks are called the abutments. and those need to be relatively strong, unfractured, and insoluble to hold up the weight of all that water behind the wall or behind the dam. And you need to have no fractures, faults, high permeability, or other weakness in the rocks. Okay, so those are our geologic factors that are important. What environmental issues are associated with dams? Behind that wall, the reservoir floods the land. So anything that was there, if you had a town, if you had all sorts of habitat, it's gone now. It's all underwater. Another issue is it traps sediment behind the dam, eventually filling it up, but also affecting the nutrient load in the rest of the river. So nutrients in the sediments are getting deposited in this reservoir and never making it downstream. Lastly, you have clear, cold water flowing out of the dam, replacing warm, muddy water that used to flow through. And the difference there is significant as far as how it shapes the land downstream. If it's not carrying sediment with it, if it's clear water, then it's going to start cutting further down into the riverbanks, as well as whatever animals live downstream that were used to that type of water. It's a completely different environment now. Generating electricity from ocean tides and currents. Okay, so it's the same idea as using the dam, in that you have water falling and you're using that fall to spin a turbine. So you either have a wall that catches water on either side as tide is coming in or coming out, or you can set up these turbines out in the ocean to spin with these ocean currents that are constantly moving. So with rising tide, the water piles up on the seaward side of the barrier and falls over toward the land. And with falling tides, it traps water on the landward side and is spinning the turbine as it falls over that wall. In either case, again, it's the flowing water that turns the turbines. Okay, that's it for this week's lecture. The second half of this chapter will be posted next week. There is no quiz this week, just one next week. And we're right close to the final, so I'll be posting a practice exam in the next few days for you to get started on studying for the final exam.